Hello, and welcome to Lecture 12, Part 1 for Life in the Universe. In this lecture and the next, so that's two sets of videos. I think there'll be three videos each. We are going to be taking a look at Unit E, which is all about some properties of energy, matter, and light that we need to either remind ourselves of or learn before we go further into trying to make sense of the universe and to whether or not there might be life elsewhere in it. And in this particular video, we're going to be taking a look at energy. Since this is the first video of the lecture, we've got an alien to have a little bit of fun with. And this is the title alien from one of the worst movies I've ever seen, The Brain from Planet Eros. Basically, it was just kind of a brain model with glowing eyes. I think in one scene they actually used a balloon for it. And the plot is essentially that an evil criminal brain from aforementioned planet comes to Earth and wreaks havoc, pursued by a police brain who is trying to capture the escaped criminal. I'm not making that up. I saw it on a double feature with an even worse movie called They Saved Hitler's Brain. You see the theme, which is, I guess, a movie that is so bad that it first reel is in color and the rest of it's in black and white because they ran out of movie money for more color film. And it's actually not just Hitler's brain. They have Hitler's head in a jar barking orders in German. I guess both of these are in the movies in the "it's so bad it's good" category. Anyway, I'll have a link to the soundtrack in the description if you want to go listen to some of it. All right, so like I said, what we're going to be doing in this this unit is looking at the nature of matter, light, and energy in a little more detail than we previously have done. Now, energy, I guess if we have to come up with a one-sentence definition for it, this is the best I've ever seen: the capacity to produce effects, which I'm not happy with, and I would imagine that probably many other scientists aren't either. When it comes down to energy, we can precisely define what we mean by different types of energy. We can measure it, the different types, and it's clear that the different types are different forms of the same thing. But as to what that fundamental thing is in general, I think, if we're honest with ourselves, we don't really have a very good handle on what it is. But the point is, we can define the specific types of it, we can measure it, and we can show that the different types of it are aspects of the same thing, which I guess is what's really important. Anyway, when we measure it, in the flavor of the metric system that we're using in this course, when we don't need special units for astronomy, that flavor of the metric system is called the SI system. And the standard unit of energy in this system is called the joule, which is not a fundamental unit in the SI system, but rather it comes from combining some fundamental units, kilograms, meters per second. A joule turns out to be equivalent to a kilogram times a meter squared divided by a second squared. The notation you see here are just two equivalent ways of writing a kilogram times a meter squared per second squared. But other than just different ways of notation for doing so, they're the same thing. If I were to take a standard racquetball, which I don't have to hold up here, but if you throw that at a speed of about 7 meters per second, where it'll cross one of the standard Wilson Hall classrooms from hallway to outside wall in about a second, the kinetic energy, the energy and the motion of that racquetball is about a joule when you do that. Now, in everyday usage, we use the terms energy and power more or less interchangeably, but there is a technical difference between them. Power is the rate at which energy is used or transferred from one thing to another. And in the SI flavor in the metric system, the unit of power is the watt. Incidentally, the watt is named after James Watt, who developed one of the early steam engines. James Prescott Joule, who the joule is named for is the person who figured out that heat was a form of energy. But anyway, a watt is simply 1 joule per second. So if you have, say, a 100-watt light bulb, what that means is that that light bulb is, under normal operating circumstances, using 100 joules per second. One last thing about units here on this slide. As you're probably no doubt aware, the United States is about the only country that isn't metric. We still use that older British system of units, or as my first physics professor, who was British, insisted on calling it the imperial system of units, because even then, back in the early 80s, Britain had been metric for a while. But even though we still use a British system, mostly there are some metric units like the watt that we do use in everyday applications here in the United States. Now, energy comes in 3 basic types, about which I'm not going to say a whole lot here. Kinetic energy is the energy that something has by virtue of being in motion. Many of you probably have seen this equation before, that kinetic energy is 1/2 times mass times speed squared. We're not going to have to do any calculations with it at this part of the course, but we will later. So I'm just showing it for you now for when we see it. But anyway, it's basically the energy has something by virtue of being in motion. And then we have potential energy, which is energy that is stored in some configuration of the physical system that can be converted into kinetic energy. And it comes in a number of varieties. And one that is particularly important for astronomy is gravitational potential energy. And I got out of the slideshow here for a second so that I could kind of demonstrate this. So a little red ball here. And if I hold the ball right here and ask you, does it have any kinetic energy? And your answer, I hope, would be no, because it's not moving. But if I let go of it, is it going to gain kinetic energy? And the answer is yes, it will, because unless something really weird happens, the Earth's gravity will cause it to accelerate and it's going to fall. Now, so I'm holding up over my hand here. If I drop it from a height of something like this, by the time it gets to my hand just outside of the screen, it's not going to be going as fast as if I drop it from higher up here. So how much kinetic energy the ball has the potential to have by the time it gets to my hand, hence our term potential energy, depends on how high up I put it in the Earth's gravitational field. And gravitational potential energy is very important for astronomy. I'm going to see if I can actually get this to do this right. I'll maybe readjust the angle of the camera a little bit. I'm going to drop it. Where am I here? Yep, here we are. I'm going to drop it and see if it will bounce so that you can see it. Not quite. Let's try it again. Trying to get it to actually bounce into the view of the camera. Almost got away from me here. So I'll maybe try it one more time here. Okay, there you probably saw it come up through the camera there if it was fairly quick. Okay, so what happens in the bounce? Okay, because it's reversing direction, which means that it must be at least instantaneously motionless, have no kinetic energy, but then it's moving again in a new direction. So where is that kinetic energy coming from on the bounce? Let's try it. Oops. Do that here. Hit the wrong thing here. Let's try this, see if this probably goes back to where I wanted. Okay, so it hit the wrong thing when I did it. But what's happening with the bounce? Well, when it hits the whatever it's bouncing off of and comes to a rest very momentarily, what happens? It happens faster than we see it, but the ball actually compresses. Yes, it's a ball with a hole in it. We'll see why when we get to stars. So it actually compresses very briefly, and that means energy is being stored in the compressed configuration of it, what we might call elastic potential energy. And when it springs back to its regular shape, that energy has been converted back into kinetic energy. And speaking of springing, not an accidental use of things, I guess the green one's easier to see. So this is a cat toy, but it's a spring. So by compressing it, I'm putting elastic potential energy into it, which I can release by letting go of it. And then that elastic potential energy is released into kinetic energy of the spring as it then springs out at least a little bit like that and starts moving. Can also do elastic potential energy by stretching. Okay, so by stretching it, I've put some um, uh, elastic potential energy into it, which I can release and have turned into kinetic energy just by letting go of the spring, which went not in the direction I expected it to. Well, I will worry about finding that later. All right, so same thing with a rubber band when you stretch it. Okay, let's go back to the share here. Now, another form of potential energy, which I don't have listed here, but one that's actually we've already mentioned, if we haven't just called it that, is chemical potential energy, where you have energy stored in a configuration of a molecule that through a chemical reaction can be released. So, for example, when you're driving your car, you're burning the gasoline in the engine. That's a chemical reaction that releases some of that energy, chemical potential energy stored in the fuel, some of which is lost as heat, but some of which goes into the kinetic energy of the engine parts, some of which is converted into kinetic energy of the overall vehicle. But back in Unit C, when we were talking about that molecule ATP, the chemical reaction that removes that third phosphate group releases energy that the cell can then use for something else. Nuclear potential energy, energy stored in a configuration of the nucleus that through a nuclear reaction can be released. And in a nuclear reactor or in a nuclear atomic bomb, when it goes really fast, that is the energy released by the decay reaction of uranium-235 mostly. Sometimes plutonium-238 or 9, forget which is the fissile one. Anyway, radiative energy, we're not going to talk about very much right now, other than just to mention it's the energy carried by electromagnetic radiation. And when we talk about light in a later video in this unit, we'll talk about that a little more. Now, one very important thing about energy is that it is conserved. The total amount of it in a closed system is constant. You only switch it maybe from one object to another or one form to another, but the total amount of it in a closed system is still the same. And so I'm going to demonstrate that by just juggling one ball here, which, I can juggle one ball pretty easily. Two, I can do a bit also fairly easy. I can do three for a brief period of time, but even doing one here while sitting in my chair here, balancing my laptop on a lap desk in my recliner is maybe a little complicated. But anyway, let's think about what happens when I toss the ball up in the air. Okay, so when it leaves my hand, I'm giving it some kinetic energy. And as the ball rises, that kinetic energy is converted into gravitational potential energy. When all the kinetic energy has been converted into gravitational potential energy, the ball reaches the top of its trajectory and stops briefly, just for an instant. And then as it's all gravitational potential energy then, and then as the ball falls back to my hand, that gravitational potential energy is converted back into kinetic energy. All right, so getting tired of that, so let me put that up. Come back to sharing the screen. And yeah, we're back here. All right, so energy is conserved. Total amount is always the same in a closed system, just converted from one form to another, transferred from one object in the system to another. Now, thermal energy or heat, use those terms interchangeably, is also a form of kinetic energy, but not due to bulk motion of something like my calculator crossing the little screen where you can see me here. It moves here, it has the whole calculator has kinetic energy. But thermal energy is, or heat is the kinetic energy in the random motions of the individual atoms or molecules in a system. So this room right now, we've got is air, which is why I'm alive. mostly nitrogen, some oxygen, and trace amounts of some other stuff. Anyway, a typical nitrogen or oxygen molecule in this room is traveling at about 0.5 kilometer per second. But I'm not being thrown around the room by them because they're traveling in random directions. And as many are hitting me, pushing me one way, as are pushing me the other, just basically notice the effect as air pressure. Anyway, in that random motion of those molecules, that is the energy in that is the heat contained in the air in this room. My calculator, which I'll even take out of the case here, um, the atoms in the calculator are fixed in position relative to each other, as typically the case in a solid. But they're still moving and that they're oscillating, they're vibrating around their average position. And there's kinetic energy in that oscillation. And it turns out that temperature turns out to be not quite the same as heat, but it's a measurement of the average of the kinetic energy in those random motions. And although we don't really need to worry about it very much, this equation, the pointy brackets mean average. So the average kinetic energy of, say, a nitrogen molecule in the room would be 1/2 times the mass times the average of the square of the speed of the nitrogen molecules in the room. And it's related to temperature this way. And then this lowercase k here is something called Boltzmann's constant, fundamental constant of nature. And we'll find out about what that uppercase k rather means in just a second. Because in order to relate this to temperature, we have to use an absolute temperature scale. Now, sometimes in this class, we're going to use the Celsius scale, which is convenient because 0 to 100 degrees Celsius is where water is liquid, at least at 1 atmosphere pressure. But in some cases, we need an absolute temperature scale. And what makes a temperature scale absolute is that 0 on that scale corresponds to the coldest possible temperature, which is where everything in the system is in the lowest possible energy state. And since you live in New England, you know that 0 degrees Celsius, the freezing point of water, is not the coldest possible temperature. In fact, this season, we've already gotten down, I think, below it a couple of times here in Westfield. Certainly very close to it. Even on the Fahrenheit scale, where 0 degrees Fahrenheit is colder, living in New England, you know it can be colder than 0 degrees Fahrenheit. So when we need an absolute scale, we're going to use the Kelvin scale. 0 Kelvin does actually correspond to this lowest possible temperature. This is what the big K stands for. And it turns out it's fairly easy to convert from Celsius to Kelvin. You just add 273 to the Celsius temperature. Now, if I lean forward so I can see it, I got a thermometer in this room, and it says it's currently 75 degrees Fahrenheit. Now, unfortunately, converting Fahrenheit to Celsius in your head can be kind of complicated because there's both a scale and a 0-point shift, but my calculator does that very easily. So 75 Fahrenheit, according to my calculator, I'm going to round it off, is 23.9. Let's call it 24 degrees Celsius. So 24 degrees Celsius, to get the temperature in Kelvin, we just add 273. And so 24 degrees Celsius would be 297 Kelvin, which makes it sound a good bit warmer. Glad it's not 297 Fahrenheit in here. All right. Now, let's shift over to light just a little bit. Okay, yep, I am where I want to. Actually, I'm not where I want to be. I don't want this. Actually, we don't need this slide is supposed to be in a later one. So this was just supposed to be the energy and temperature stuff. Okay, yes, so that's right. Sorry, when I was editing, I didn't remove that last slide here. So anyway, here's your attendance secret code. We'll get to that other slide when we really need it. Hurricane Diane, hurricane in 1955 that caused an enormous amount of flooding in Westfield and in New England in general. Came a week after another hurricane had already dumped enough rain to saturate the ground, and then Diane dumped 18 inches of rain on Westfield. So quite substantial flooding here at the time. So hopefully we won't have another one of these for quite a while. But anyway, this shows its track. No satellite images of it because there weren't any satellites in orbit in 1955. Anyway, Hurricane Diane is our attendance code for this video. Sorry about that extraneous slide, but we'll see it when we need it. All right, see you in the next video, where I believe the next thing to take a look at is atomic structure, and then photons and light come later.